Okay, thank you. And I want to thank Manuel and his great organizing team for organizing such a nice conference and a nice metric for this that just for the very last talk of today, there are still so many people. I didn't count with that many. And in return, I wanted to make this little lively, as you've seen, so there will be some jokes running around, and especially perhaps we can compete then later among the speakers who will get more likes on YouTube. So that's quite new. So I'm going to talk about factorization of non-commutative polynomials. I will explain you problems and settings and all that. And okay, sometimes you have to read between the lines. And I think this is the 8th time commemorating the very algebraic character in the pop industry as a Darth Vader. So this is a plan of attack for today. And let's start with very beginning. As everyone knows, we teach our students that yes, most of the time students in the first year work with unique factorization domains, and it goes even to regular local rings somewhat later in the story. And sometimes we also give examples that kids, not everything in the world is UFT, and usually we're given this example. Or say in the context of algebraic geometry, often we just elementary produce this example. So there are UFDs, there are non-UFDs, but for most of students, non-UFDs are something exotic and something far away. Okay, from the 90s, Anderson and his collaborators started to doing really deep investigation of properties of factorization of various integral domains. And for instance, note this book here, and there is a whole zoo of properties which exist for domains, and the natural weakening of the unique factorization domain property is FFD, which is finite factorization domain, but of course you can imagine that there are domains where elements might have also infinite number of factorization. I think you will see them quite funny. So we take the classical book by the Dark Lord of the Seed, Nathan Jacobson from 43. We'll open it, and we know that non-commutative left and right principal ideal domain is a unique factorization domain. Let's take the perhaps championed by likes among the algebras which were mentioned in all the talks of this conference, the rational Weil algebra. So this is a ring of linear partial differential operators with coefficients in the ring of rational functions, like think for characteristic 0 at the moment, and we follow, of course, the dark ways of the force, and we believe Professor Jacobson, and we know d square is d times d, it is UAD, so it is a factorization. So far, so good. Another Dark Lord of the Seed, Paul Maurice Kohn, in the paper from 63, in a nice journal, claims that a free associative algebra generated, say, by n variables is a unique factorization domain. Very nice. We pick this polynomial and bravely extract x to the left. So we trust the dark side of the force. So this is a unique factorization. So let's recall. Yeah. Haha. It's not me, it's them. A very good question, and this is approximately 1/3 of my talk answering this, but merci beaucoup. So, recall, Kohn and Jacobson claim these things, but, okay, we have extracted x to the left from the x expression, bravely. Equally bravely, we can extract it to the right. Okay. Similarly, over the rational Weil algebra, after some work, you see that actually for d square, we can give characteristic 0 actually infinitely many factorizations. So here we have another one, and it's not so big work to show that there are only 2 factorizations. Okay, 1 or 2, then perhaps something in it, but here we've got infinitely many of them. So where is the problem? Where is the mistake? Well, there is no mistake. There are 2 different notions of association up to which we work. So consider these two following definitions. Of course, in linear algebra, we teach our student both this one, but also we can produce this one, left similarity, especially if you grow up from ring theory. So it means that left similarity includes the isomorphy of these cyclic modules presented by principal ideals. Exactly, one can also show there is a notion of right similarity. As soon as we are commutative, the world is fine. These two guys are equivalent. But in general, of course, we have only one implication. So we have at least two choices up to which association relation we'd like to work. And for a number of reasons, me and my colleagues, we prefer to work with the usual one, with the linear algebra one. One of the reasons is that actually we work in algebras of operators. And there the multiplication already stands for composition of operators. So there is no need to introduce composition of compositions for our reasons. And secondly, well, I'm not aware of the fact that this guy is decidable in general. I doubt very deeply. You have the answer? Yeah. Well, even if it's decidable, I think it's hard. Yeah. So these are the setups. We have selected the right association and we continue to work with it. Well, actually, motivation is one thing one has to start with, but many interesting, deep and important problems boil down at some point to the necessity to factorize. In some applications you need to have all factorizations. In some you have to need some factorizations of spatial type. In some you need just to know irreducible or not. Right? And one of application is a partial module decomposition. I hope this is not too involved, but the idea is if we have a polynomial which has finitely many factorization in G, I, and H, I don't really impose that one of them are irreducible, then for instance, if we add left ideals L and a principal ideal R generated by this F, then we can realize this guy, this ideal, as intersection of this ideal where we just take the right factors HI. This is very easy to see. And then we have this surjection. You know, this is needed in some problems, and it is not that seldom in practical applications that these guys are, this collection, these guys are pairwise comaximal. Then we even get this isomorphy, and therefore from this module we have found an epimorphism to a direct sum of smaller modules. And this is of importance, and I will give you an example perhaps more convincing than just this naked theory. And I will also talk about the factorizing Grobner basis technique. Let me just tell you that what it gives you back, you start from a left ideal in a somewhat similar way as described here. It delivers you a collection of, say, left ideals such that your ideal is contained in their intersection. Yet another hot topic is the closure of ideals with respect to order sets or contraction. So there are 1001 names for this phenomenon. But think about this formula. So we are in a left ideal and we are looking for such elements from the ring such that there exists a left multiple of this R which lies in L. So this is a complicated job to do. It has many deep meanings and even factorial meanings. So this is precisely the generator of S torsion submodule of the associated module, and provided we have a factorization routines, then we can approximate this closure by taking elements from the ideal, compute factorizations of them, and of course look whether there are factorizations of this form where Si, even without prime, is in S. So we know then this Gi will be sitting in the closure. So this is example for some factorizations or factorizations with some special meaning. So let's go to the battleground. So Anderson et al. In the 90 gave the following definition, which I am not going to read, but you can if you wish. Yes, the main things are underscored in red. yes, finite number of factorization up to order and associates. So with Jedi Meister Jason Bell and my former Padawan Albert Heinle, we gave the following reformulation of this definition in 17. So, by the way, I'm following the tradition of giving the references inline. I have additionally a couple of pages of references in the end. I don't pretend them to be conclude. So this one, permit me to read. We have a ring which is a domain, and it is a factor, finite factorization domain if we have non-zero and non-unit element, and it has at least one factorization into irreducibles, and there are at most finitely many factorizations into irreducible up to multiplication of the irreducible factor by central units in A. Central means those who commute with the whole algebra. So this is reflecting the association relation which we want to. And the theorems. Actually, this will be the next slide, but every one of us, having met on the way the necessity to factorize something, say in finitely presented algebra, everyone would try an ansatz. Right? We collect the terms, we multiply them out, we use the writing rules or modulo our relations of the algebra, and then we end up with a system of polynomial equations in commuting variables for our ansatz coefficients. But the question is, will the solution have finitely many solutions or not? And this is a big question. And this is precisely what has to do with finite factorization domains. Therefore, any procedure which appeared in the last 200 years for factoring elements in noncommutative rings is a procedure, and this is the first proof of termination. I have to say, Tsaryov in 91 gave a very complicated proof for the first polynomial Weil algebra. If you know more results in between, then please let me know. And here's a statement. If we have an algebraically closed field and a K algebra A, if there is a finite dimensional filtration on A, such that the associated graded algebra with respect to this filtration B is a domain, not necessarily commutative, then A is finite factorization domain. And if you want arbitrary field, the following version gives it. We have a field in a K algebra if there is a finite dimensional filtration such that the associated graded algebra tensored with the algebraic closure of K over K is a domain, then A itself is a finite factorization domain. So for the proof, I refer you to the paper. It's algebraic geometry Shafarevich style. So it's far from being evident. And actually, when we started the joint work, we expected more conditions to come in, but the only thing you need is the existence of finite dimensional filtration such that associative graded algebra is a domain. So in particular, rephrasing polymerase con, the free associative algebra is not UFD in our setting, but it is finite factorization domain over any field K. So this is more or less formally, perhaps I propose you rather not to read it. This is a classical ansatz by using the filtration. And now it is with this theorem for these algebras we have provided proof of termination of all these algorithms. Later I will say some results on the complexity and all that. In my opinion, the story of polynomial factorization in commutative case, it took many years and it resulted in a nice complexity, but the algorithms are very intricate. Perhaps in order to achieve this nice, or somewhat in the direction of this nice complexity, one has to take noncommutative algebras, say their isomorphic type, and do something very specific for these algebras, similarly like it was done for the polynomial ring. So this is I don't see a universal way to get the good complexity. Well, that's life. So perhaps one has to do it separately for the while algebra and for shift algebra, and then over them. So this is a hard job, but still, in theory, we have an algorithm which returns all factorizations, finitely many factorizations of a given element. So these algebras form my, so to say, home category. Spent many years working with them. These algebras are known as named algebras of Sobol type, known to some part of the PBW algebra from Polynomials, known to some other part of the algebras, or also G algebra, where G stands for Grobner. What is important that all algebras are Noetherian domains with nice Grobner basis theory, and perhaps this is the most natural generalization of polynomial rings being commutative, because they share really many properties, ring theoretic and homological, connected to them. Instead of reading the definition, you have seen the relations, but most of ubiquitous algebras of operators are G algebras. You have seen this for sure, and on the poster you might see in the integration. Also, all universal enveloping algebras are finite dimensional Lie algebras are over there, quantum groups, and so on and so on. Of course, we extend this category by factors by two-sided ideal, and then, for instance, we get all Clifford and yet more quantum groups. So it's a big and nice category, and it has a nice Grobner basis theory, and it has an implementation in singular plural. So, as a result, it is a test bed for me personally and my colleagues when we are trying to address finitely presented algebras, because about these algebras we know nearly everything, and even over them we have some problems of different nature, algorithmic and theoretical. So, dependent on the ground fields, all these algebras and their subalgebras are finite factorization domains, so we can factorize, and I think many of you will be glad to have an algorithm to factorize over algebras of operators. So, we take this algebra, polynomial of degree, say, d, and leading monomial of G has exponents alpha 1 to up to n naturals. Then, in order to find all factorization of a polynomial G of degree d with this leading monomial, we need that many operations. This is a very recent result. This shows how complicated this story is, but this way is by using this more or less universal ansatz, which I described several pages before. The ansatz everyone could try it. So this is what we need. So the factorization is implemented for all the algebras I have described before, all G algebras, so try it. And you can really, black holes. You can try the algorithms and it can compute this stuff. So, go back to some factorizations. Recall it was the closure of an ideal with respect to the set. So let's consider Legendre polynomials, consider it as a special function. So the corresponding algebra of operators is a discrete part, which is a shift algebra, and a continuous part, which is a while algebra. So working in this tensor, we're working over characteristic 0. So classically, so everybody knows that two classical annihilating polynomials are Legendre's and Bonnet recursion and Legendre's differential equation, which are already written in terms of operators. So what we'd like to have, we take our OR set to be just polynomial ring and two variables deprived of 0, and consider the left ideal generated by these two guys. Then, by some dark magic, actually Grobner with respect to some orderings, we find that there are in the ideal generated by these two guys, we can see this polynomial which factorizes uniquely into this way, and this polynomial which factorizes in this way. So this was in S, this one is also in S, hence this and these guys are sitting in the closed ideal, and independently which one you add to the ideal generated by P and Q, you arrive to these three generators, which is already a Grobner basis, and I conjecture that this is really the whole closure of L. Well, this is still a conjecture. Hopefully some new algorithms will confirm this. But this is the merit of computing some factorizations, and this was applied to this example. So, Manuel, the closure of Legendre is not yet known, or you know it already? Closure of Legendre, desingularization. Okay. In 2. So is it known or not? Aha. Okay, so it's still a conjecture. But you have seen that the classical ansatz has described complexity, which is high. The question is, can we do better? The answer, yes, we can. But I decided to split this part of the talk. So there is a technology called graded-driven factorization. It means if your algebra of operators allows some nice grading, say z to the power n grading, then you can do much better. You can do much more clever ansatz. And actually, this story consists of these 3 papers. This and this, so this is already available online. This will be available online, hopefully in a couple of days. I just leave the references so we can do this by now, even for G algebras which admit a grading, then we can do much better. It is from the technological point of view. Now, promised some bounds. So, in our situation where our algebraically closed field, we have a filtration. It's fine, it has to be finite dimensional, and let's G V of D be the gross measure of it. Then we have that many distinct factorizations in 2 elements at most, and at most this number of total distinct factorization. You see this is exponential, so this can be arbitrarily bad, but here's the difference between the algebras, because the growth function goes inside. So G algebras are algebras of polynomial growth, therefore you have just this Pohammer, and free algebra has exponential growth, therefore you have this one. So perhaps the worst case will be, it is clear that our free algebra will get really many possibilities, and in one of the papers with Albert Heinle, in the first homogeneous, in the first while or q-while algebra, we take a homogeneous polynomial with respect to the z grading, means x gets degree -1 and d gets degree 1, and then this guy is homogeneous with respect to this. So theta is Euler derivation, x times d, and phi is either x or d. So all the homogeneous elements with respect to the z grading are of this kind. Then if d is the degree of this guy's polynomial in theta, then we have that many different factorizations. And just for orientation, the rising or falling factorials are worst cases from our analysis. So it can be that big. So, factorized Grobner bases, perhaps you have heard about them. The principle is very easy. You are running sort of Buchberger algorithm, and every time you have a new candidate for your basis, which enters the basis, you factorize it. If it factorizes, you start branches where you add 1 factor and says the others are not 0. At the end, you get a tree, and this gives you of course, it has been proved, there is a vast literature on the subject. It gives you a set of ideals. I will tell some more about this. So it is used in algorithms for computing primary decompositions in a commutative case, and it is surprisingly good. In many cases, running factorizing Grobner, although the idea is very easy, it already gives you a decomposition very close to primary decomposition. So it's from the practical experience. And then there are many implementations. Perhaps one of the prominent, one of the fastest one is in singular.
Well, in non-commutative case, we can do factorized Grobner basis as well, and in non-commutative, we don't have a direct analog one to primary decomposition, which every one of us desire. And thirdly, you remember one of the first slides, even more as in the commutative case, we need to decompose modules, but we lack most of instruments because most of commutative stuff does not generalize. So, rough description what happens. In roughly speaking, we're working over C, then ideals and commutative ring correspond to varieties. Up to certain approximation, we can also think about ideals, non-commutative ring and solutions of correspondence system of equations in the certain space. There is a formal notion of solutions via this solution functor, which is a K vector space, and divisors in commutative rings we will associate with right divisors for non-commutative rings. However, our ideals are left ideals. You can do the whole stuff also the other way around. And so the difference in non-commutative factorized Grobner to commutative factorized Grobner, instead of only maximal right divisors, we have to consider all possible non-unique maximal right divisors, because of the non-commuting we have to take many things into account. But so the main property of the factorized Grobner basis in the commutative case over C is that not only your ideal is lying in the intersection of the output, but their radicals coincide. So it means geometrically you're getting components out of factorizing Grobner basis. Well, we don't have a nice notion of a radical yet for left ideals, but even from this fact, we infer that this map will be the surjective homomorphism of A modules, and therefore, applying the solution functor, we know that solutions of this guy are contained in solutions of the original guy. As I said, it sometimes happens that these guys, which are output by factorizing Grobners, are co-maximal, and co-maximality allows us to write this situation. So we have identified by means of factorizing Grobner basis a direct sum of smaller solution spaces inside of a bigger one. If you're not yet convinced, let's make an example. Let's take some innocent order 2 polynomial. This is from the dissertation of Haritsai 2000. So order 2, and here's polynomial. Let's make it over C. So this guy has precisely two different factorization, where the rightmost factors I denote by Q1 and Q2. We run our implementation of factorizing Grobner basis, and it returns us just two components, one generated by Q1, one generated by Q2. Well, not that surprising, perhaps not that fancy from the first point of view. And it's important that the ideal generated might be strictly contained in the intersection. It's not equal. The intersection is generated by two guys, and this is just the one. So A is the first while algebra, polynomial 1, we take some left A module, then we apply the solution factor, and it turns out that these guys are comaximal. So we have a direct sum here, and for arbitrary F, for arbitrary left module, we know that this direct sum of guys, they're one-dimensional vector spaces, is contained over here. Well, P has order 2. By Koshikova-Levskaya-Kashivara, we know that the space of holomorphic solution at a generic point, it means outside of singularities, which are 3 or 6 points here, is the direct sum. And for holomorphic solution, we have already computed them. And, well, thanks to factorization and factorizing Grobner basis. So I think I'm close to the closing remarks. So what we need to, we'd like to extend criteria for non-commutative finite factorization domains, because there are still some examples which do not satisfy the conditions of the theorem, and we still don't know whether there are zero divisors or not. Computing zero divisors in a finitely presented algebra, I am not aware that this is decidable. It's a big question, although it sounds absolutely basic. Yeah? So, of course, having
rings like integral differential algebras which have zero divisors. The next question is how this will correspond to finite factorization rings. Actually, we are working right now on generalization of the whole situation for finitely presented algebras. And again, my philosophy is factorization is the first step. The second step is factorizing Gröbner basis. These two things are coming together because factorizing Gröbner basis gives you a partial decomposition of the module and can be done over fairly general rings. Then the actual output of factorizing Gröbner basis, it actually has more information which we still don't quite understand. In the commutative case, it allows to treat inequations, that is semi-algebraic sets. We have similar stuff in our case, but we honestly still don't understand what does it mean. There's beautiful information, and as I told you, we work like classical computer algebras on theory, algorithms, proofs, complexity, and implementation. Last but not least, these guys are implemented. So I might invite you to try, and you know, software is bug-free until it is used. So thank you very much. So the question was, what is the complexity of factorizing Gröbner basis? It amounts to finite number of calls to the Gröbner basis, so it's at least double exponential. It's not yet clear, and honestly, well, double exponential is bad enough, already bad enough, because it's really the branching in the non-commutative case is much more intensive than in commutative. For us, it was rather interesting to see that it sort of terminates on practical example, and therefore we have some heuristics to do it in a more clever way. On the other hand, the non-commutative case is more rigid than commutative. It means if you add guys, new generators to ideal, many ideals will contain one, and this is in a very fast way. So no definite answer. Whether there is an additional exponent, perhaps in over free algebra where we have exponential number of factorization, then for sure. Yeah. Yes, with our notions associated up to central units. If we take Jacobson, then this is one factorization. For Jacobson, this is just one factorization. Good question, thank you. Imagine the diagram where you multiply. So this precisely, these two factors equal to two factors, gives you the morphism and gives you the isomorphism. Yeah, thank you.